Good morning everyone, my name is Jesse Reed, and for today's 10-minute maths lesson I'm going to be looking at applied geometry, specifically angles of elevation and depression. So a bit of trigonometry revision before we can get on to angles of depression and elevation. So specifically we need to know about the components of a right-angled triangle. For right-angled triangles, of course, only one of the angles within the triangle will be a right angle. Opposite your right angle will be the hypotenuse. It's one of the important rules to remember. So the remaining two sides rely on where your theta angle is. So the side that's furthest away from theta is the opposite, and the remaining side is the adjacent, which ironically runs adjacent to your theta. So now some of the trigonometric equations that you need to be familiar with before we can cover angles of elevation and depression. So in high school and college, I'm sure everybody's been drilled with the SOH-CAH-TOA. So SOH is sine theta is equal to opposite over the hypotenuse. CAH is cos theta is equal to the adjacent over the hypotenuse, and TOA is tan theta is equal to the opposite over the adjacent. So angles of elevation and depression. So most important rule for this is that you always treat your horizon as 0 degrees. If you are looking at something above the horizon, you are working with an angle of elevation. As you can see here, you'd be standing down here and you're looking at something up in the distance up here, you have an angle of elevation. With angles of depression, you are looking below the horizon. So here our horizon line is here. Pretend you're standing at the top of a cliff looking down at something. You then have an angle of depression. So with angles of depression, it's important to remember that your working right angle triangle is down here. So you'll need to work out your theta from your angle of depression. So how do we measure angles of elevation and depression in practice? In practice we use a clinometer. Now I have a gun type model pictured here. So the way this works is it has a protractor wheel, there's a counterweight attached to your protractor wheel. To take your measurement, you hold your trigger in, you aim along the sights of your clinometer at a target that you're interested in knowing your angle to. When you're holding the trigger, the counterweight is affected by gravity and causes your wheel to spin. When you release the trigger, it holds the angle measurement and you read it off here. So when I was in high school, I found a lot of the examples that were given for any exercises to be a bit dry. Lots of stuff to do with hot air balloons when it came to trigonometry. So I thought it would be interesting to have a look at something out of a movie perhaps, and I chose the BFG. So the BFG is a book from Roald Dahl. So here we have the big friendly giant, and next to him is Sophie, the orphan child that he decides to take care of. So I thought it would be interesting to find out how tall is the BFG. So we've got a line here with our measurement of interest as x. Thanks to some internet wizardry, I found out that the actress who played Sophie is 1.5 meters tall. Using this still shot, I turned her measurement on its side and I got 2.5 distances worth, which gave me a measurement from Sophie to the BFG of 3.75 meters. So as you can see, we now have a right angle, and if we use a measurement from the top of Sophie's head to the top of the BFG's head, we have our hypotenuse. So I thought that maybe Sophie herself is trying to see how tall the BFG is, so she's using a clinometer to get an angle measurement, and we'll take the measurement from her sight line to the top of the BFG's head. So when I used a protractor, I got an angle of 66 degrees here, which will be our theta angle. So a review on what we know. So we know our adjacent measurement is 3.7 meters and our theta measurement is 66 degrees. What do we want to know? We want to know the height of the opposite measurement. How are we going to do this? So remembering back to the trigonometry review that we just covered. We're going to use TOA, so tan theta is the opposite over the adjacent. In this particular format, it's a bit difficult to actually picture what the opposite measurement is going to be. So I used some algebra to rearrange the equation. I multiplied both sides by the adjacent, and this gives us that tan theta multiplied by the adjacent is equal to the opposite. Therefore, the opposite is equal to the adjacent times tan theta. So now that we know our values and our equation, we're going to substitute the values that we know into our equation, which you can see down here. Next, we want to solve the adjacent. So we have our opposite is equal to 3.75 times tan of 66 degrees, and that gives us a result of 8.42 meters. So is this how tall the BFG is? No, you need to remember that when you're taking a clinometer reading, you're taking it from your eyesight's horizon. So you also have to remember to add in your height to your final measurement. So we add Sophie's height, because she's the one taking the measurement, of 1.5 meters to our 8.42 meters that we got from our equation, and our result is 9.92 meters. Interestingly enough, in the book, the BFG, Roald Dahl reveals that he is only 7.3 meters tall, so Hollywood has embellished somewhat on how tall the BFG actually is. So for our next example, I thought we could use the angle of depression to measure a distance. I quite enjoy the movie The Toy Story, and I remember a scene in it where Slinky the dog is trying to rescue Buzz Lightyear and Woody and trying to bring them back into the truck. So to do this, he stretches himself out, and the toys in the truck here are holding his back end, and his front end is down here trying to rescue his friends. This particular still that we have is the longest distance that Slinky is before he gets catapulted back into the truck. Again, thanks to some internet wizardry, I found that the height from the toys in the truck down to Slinky's head was approximately 1.2 meters. I thought we could take the measurement as if it was the toys in the truck trying to figure out how far away Slinky is. So they use their sight line as the horizon, and they're looking down towards Slinky's head end, and they get a measurement of 14 degrees. So we need to remember that this here is our working right angle triangle, and then we're going to need to be able to calculate theta before we can work out any measurements. So to calculate theta, we remember that our horizon line is 0 degrees, and that this is perpendicular to the vertical side of our working right angle triangle, of course presuming that the road is flat. And this gives us a right angle, which allows us to calculate theta. So theta can be calculated as 90 degrees minus our angle of depression of 14 degrees, and we get a theta of 76 degrees. So I'll review now on what do we know. We know that theta of our working triangle is 76 degrees, and our adjacent measurement is 1.2 meters. What do we want to know? So we want to know the length of the hypotenuse, which is x. How are we going to do this? We're going to remember back to the trigonometry review, and car comes to mind, so cosine theta is equal to the adjacent over the hypotenuse. This again is a bit difficult to work with, so I've used algebra to rearrange the equation and make it a bit more friendly. So what I've done is I've divided both sides of the equation by the hypotenuse, and then I have divided cos theta to both sides, so that balances the equation. So our final equation is the hypotenuse is equal to the adjacent over cosine theta. So now that we have our working equation, we're going to substitute in the known values into the equation, and that's what it looks like down there. So now we're going to solve the hypotenuse. So to solve the hypotenuse, we have 1.2 meters divided by cosine 76 degrees, and that gives us a result of 6.2 meters. 6.2 meters. No wonder our poor Slinky Dog couldn't stretch any further. So, as a bit of a take-home message, maybe animators and graphics designers should use applied geometry to double-check the scale of their characters. Thanks for listening, everyone.